All right, good afternoon. I'm Chris Pistorius. I'm Associate Department Head and Postgrad Professor in Materials Science and Engineering, and also co-director of our Center for Iron and Steelmaking Research. Welcome to the College of Engineering webinar series, Faculty Insights, a 20-minute briefing. Thank you all for being here today. This is a virtual series in which faculty from across the college share insights into their research, the impact of the research, and perspectives for the future. So after the 20-minute presentation, you will have the opportunity to have your questions answered by our speaker, who today is Mohadeseh Taheri-Mousavi, who's Assistant Professor of Materials Science and Engineering, and her presentation is titled Exploiting Additive Manufacturing to Design Alloys with Unprecedented Properties Using Machine Learning Techniques. And Mohadeseh will explore how additive manufacturing is revolutionizing the production of metal components for critical applications in aerospace, automotive, biomedical as examples, and the unique conditions during especially laser-based melting and rapid solidification opens up the possibility to exploit those processing conditions with custom alloys to achieve really unprecedented material properties. To plan this to pick the right material, that requires considering many different material variables, compositional variables, and processing conditions. So Mohadeseh uses advanced machine learning tools to navigate through this multi-dimensional design space, use many different data sources, and this all helps to accelerate the design cycle and reduce alloy development costs. Mohadeseh joined us as an assistant professor in 2022 after postdocs at MIT and Brown. She had earned her PhD from EPFL in Switzerland and her bachelor's and master's degrees from Sharif University of Technology. She has been really active in getting her research going here. It's been a real joy to have her in our department. She does other things like take her group on walks in the park. She helps to develop the whole person, research and socially. She has received fellowships from the Swiss National Science Foundation, and her research here has been supported by major sponsors, including the Navy Nuclear Lab, NASA, DARPA, and the Army Research Lab. In 2 weeks, she will be recognized also as an early career distinguished presenter at the Materials Research Society Fall Meeting. So before I turn over the screen to Mohadeseh, I would like to remind you, our audience, to use the Q&A feature. You'll find that at the bottom of your screen to submit questions to Mohadeseh regarding our presentation, and you can do this at any point during the presentation. After the presentation, Nikki Bernardi, who is our Senior Director of Development in the College of Engineering, will moderate the question and answer session. Mohadeseh, thank you very much for being here today, and over to you.
Thank you very much, Chris, for the kind introduction. Thank you, everyone, for joining me in this seminar. It's my pleasure talking with you and for you. And I apologize for my sound. And if I need to mute for a cough, I'm still recovering from a severe flu, but I didn't want to miss joining this opportunity and talking with you. So I share my screen, hopefully. Okay. I hope it is okay. Okay. So as Chris introduced, we are interested in, me and my team, we are alloy designer. We are computational alloy designer, and we are interested in designing structural alloys which are used in various industrial applications from aerospace and car industry all the way down to microelectronic devices. So, but how do we traditionally manufacture and design these alloys, and how it has been changed? Traditionally, it was a research scientist who had some idea or intuition because of previous trials, and there was a few like iteration, and casting was the main manufacturing technique. There is a huge interest recently into using additive manufacturing in manufacturing of these structural alloys. Why? Because at some point we have reached to saturation that how far and how fast we can make our, for example, our airplanes, and we wanted to contribute to better performance of these structural to these industries by making material better, by bringing high performance to bring us fuel and material efficiency. But when I say additive manufacturing, we are mainly focusing on two main technology, which is laser powder additive manufacturing. For example, there is one which is directed energy deposition. In this technique, the metal powders come from these tubes, and then there's a laser here which melt the required powder, additional powder, and then you melt your component layer by layer. In the powder bed fusion technique, there is a metal powder stock, and then one layer of powder is spread, then the laser pass and melt the required area, another metal powder is spread, layer of powder is spread, and you build your component layer by layer. So why people are, or why we are as alloy designer interested in additive manufacturing? Because of two main opportunities. One is that we have new processing condition. Consider here, we have, after we add elements together, you have a global melting. And when you put it in the mold, it's a slow cooling rate. And if we want to do any post-heat treatment, we must to do globally. Here, we just locally melt the additional powder, and we have a fast cooling rate because of its laser interaction, and we have also the ability to locally do post-heat treatment. The other opportunities is because we can have a gradient alloys. Here, when you choose the composition to be melted and you choose the processing, the composition and macrostructure, which is what you can see under the macroscope of alloys, are fixed through the component. And if you want to change it systematically, that I will tell you why, then you have to do systematic post-heat treatment, mechanical or thermal. Here, however, at the voxel size resolution during printing, you can tune the feed rate of the powder from these tubes. Therefore, you can change the composition and you can change the heat. Therefore, you can change the macrostructure. So therefore, at the voxel size resolution, you can make gradient alloys. Is this something first a research in our lab, or is it something in the industry? You can already see the evolution of Raptor from a SpaceX, and this is the one from August 2024. And you can just by comparing this, the 3D printed version, that how much you saved weight of this component. But what are the challenges and big opportunities that we are interested to answer? One is that now we can print these alloys, our alloys, with a micron size resolution for this industrial application. However, the properties have a lot of uncertainties. We cannot reliably achieve the properties that we aim for or what we could achieve with casting. So achieving reliably the properties that we could achieve with casting is one main goal now. Second is that, as I showed you, we have new opportunities and new tuning knobs during the printing or processing of these alloys. Maybe these new opportunities can cause some new design that we could not do it with casting, and we achieve some unprecedented properties that then that is what we can achieve now and we couldn't achieve before. And third is that maybe to achieve the first and second goal, we need new design concepts and new methodologies that to help us to achieve our design targets. So I will answer the three opportunity by taking you to the journey of designing high temperature, high strength, additively manufactured aluminum alloys that we take in our group. So first give you a background is that consider aluminum after steel is the widest used structural alloy in industrial application. It's in the body of your airplane, especially it's in transportation industry because it's a light element and has a higher strength. However, whenever the temperature a little bit goes high, between 100 to 400, in these applications like fan blade of jet engine or piston of combustion engine or vacuum pump, you will see that there are other alloys. Like here, if you go from airplane and if you enter any airplane and see from the window, all the fan blades are from titanium. Why it is the case? Because aluminum is a light element. You have seen soda can, yes. But if you want to use it for high temperature application, you should add high melting point element to the composition. This element, when you melt all in casting, it's sediment to the bottom of cast, there's a manufacturing challenge. So we thought when additive manufacturing like laser powder bed fusion came, maybe this class of alloy can emerge because you do not melt everything together and you just melt layer by layer. And aluminum is a choice because it has a higher strength, resistant to corrosion, lightweight even compared to titanium, and much lower cost, 3 to 10 times lower cost than titanium, for example, for these fan blades. And titanium is a bit overqualified for this application. So, but when I started this project, in fact, since it was the time when I was a postdoc at MIT in 2020, the question was that what are the available options in the market? At the time, although aluminum is very vibrant class, however, you cannot print it because you see these cracks during printing aluminum, and we call them hot cracks. And because of that, a few class of them commercially you can print. And the most famous one was the scam alloy that has a scandium in the composition that has 2 orders of magnitude higher cost. But even the available options, all of them, their strength significantly drop. That for me, the target was 250 degrees C, something for a fan blade of jet engine. And at the time, the benchmark or the record alloy that didn't have the highest strength but could sustain the strength much better than other option was an alloy which was patented in 2019 and was called Alloy 1 and had 5 elements: nickel, erbium, zirconium, yttrium, and ytterbium in it. So the idea was that can I have an alloy that has a better performance compared to this alloy? So as I said, you have to design it to inhibit the cracks, and we do it by controlling the solidification characteristic, means the time and temperature range during solidification. But we also had an idea to improve the strength of an alloy that I share it with you here. We found out if you are in these 5 elements, like compositional space, first you have to choose the composition smartly. If you choose that composition smartly and you are in a correct composition zone, then if you do additive, if you apply rapid solidification, like what happened in laser powder additive manufacturing, you can block the what you can see in the macrostructure of alloy, means what you can see under the microscope in a metastable state. That state is very useful because after printing, then you can heat the sample or age the sample, and then you will see some features inside the sample that are nanometer scale. If the same composition you cast it or slowly solidify, you see these features at the micron scale. You see orders of magnitude different. And why it is important? Because we know that if these features, which are called precipitates, are smaller, the material becomes stronger. So this is, although this is our main idea, and we finally made this work, but designing alloy is a complex task. For example, if I wanted to come up with any new recipe, means any new, I say which element should be how much concentration, you should think of this alloy should go through the powder processing, through printing processing, through post-heat treatment processing, that each of them have their own parameters. And this by blocking, like by by fixing the processing parameter, you fix what you can see under the microscope of alloy. And there are many features that you are caring for that control the properties that you are seeking for. That for us was creep resistant, high temperature strength, and we didn't want to see those hot cracks. So finding the better solution than that, like record alloy, is like doing a domino game. Whatever you try to make it better, you destroy other properties. And our idea was that to combine our computational technique with machine learning technique to help us explore this design space and connect this compositional space to properties, do forward prediction. And after we develop these functions, which is surrogate models, we use optimizers to do inverse design, means we put a target property and tell us what is the best recipe. So in fact, by only 40 samples, we show it in this paper, which is now online, we found a new recipe for the alloy that we ordered a custom powder, we printed, and we showed that our strength was 50% higher than that record alloy, and the same strength as wrought aluminum 7075, and it can sustain also its highest strength even at 400 degrees C for 48 hours. But the big news also is summarized in this figure. You see, it's the same composition was casted, the strength was 5 times lower. So it means that additive manufacturing has some tuning knobs that if you use it, you can achieve some unprecedented properties that you could not achieve with casting. We further improved the properties of this alloy because we had a lot of industry interest. The as-built ductility of this alloy when you do tensile test was very limited. And this is very important if you really want to print larger scale of this alloy. And we improved the ductility of the as-built to 20%, while only we sacrifice 25% in the strength. We further enhanced the strength of this alloy by introducing new features also in the microstructure to partition the grain and somehow block this plasticity and make it stronger. And we can achieve the strength of 540, which somehow we shattered the roof of properties of cast alloy, and now we are approaching the strength of a steel. We call it internally a steely aluminum. So, but imagine if we can replace steel with aluminum in this application, in this strength range. Aluminum has 3 times lower weight, and you can see how much we can save, like in energy and in weight of the material, and in general in material use. So with that, we are now upgrading these alloys for, if you use it for larger scale production, for previous properties, and also include additional properties for a specific industrial application when it is needed. So this is now a start of a large journey. But the other thing, but we further became interested and we got other requests for designing other type of alloys. For example, we entered the design of high entropy alloy, with, which was tungsten-based high entropy alloy, which had rare earths or refractory elements. The previous alloys that we designed, we had a very good database. All those designs were fully virtually designed and validated in experiment. But here we didn't have a good database. In these cases, you can do some multi-scale simulation, but you cannot fully rely on them 100%. You may have some modality of experimental data, and you may, for some of the elements, you may have constraints because of processing from ore or making processing powder from them. And you want always, for a design of this alloy, you want to combine all these modality and field of data. And usually there is also a human or literature who have also some knowledge, and you want to combine and decide what next experiment to do and do the test that finally you design or find the recipe for the alloy for that target property that you are aiming for. But how can we shorten the loop of this iteration and make it the whole process more efficient? We thought the best framework to accept all modalities of data is human language, because we all, as a human, we understand text, we understand images. So maybe an audio and video, then especially with the rise of all these large language models in other fields, and I'm sure many of you have used ChatGPT for your everyday use, the question was that, does this large language model, such as GPT model, can learn the grammar of physics of alloy and do forward prediction, means connect composition to a structure, to property, and if it learned, then can it do inverse design for us? So in fact, we had a very good database for aluminum. We already changed this database into sentences. Okay, there are some tricks how to do that, but we have a block of what is the task prediction means for forward prediction, block of composition or processing, then a structure, and then property. And we train our model, and in fact, we found it's super smart. If you prompt it with composition or only composition and a structure, and you predict a structural property or just a property, you see that it has a very high accuracy in prediction. But does it also do a good inverse design? In fact, then we found out, although with all conventional techniques, machine learning techniques, you need usually one algorithm for forward and one algorithm for optimization. If for generative AI or large language model, one framework can handle both if you train with both data. Just we change the task into generating, you now prompt it with property or property and a structure, and we found that it successfully could do with also the same high accuracy, do the inverse design, and especially if you only prompted with only property, we found out it systematically can find all diverse solution that can achieve the same property. Because as a metallurgist, we know that if you have a single property, there are several paths of composition and a structure you can achieve the same property. And we found out this probabilistic model can find out all these solutions systematically, and that is exciting. The detail of that is in this paper, which is published this summer. And this is very exciting, as I told you, that one of the interesting direction that is now open is designing gradient alloys. First, why gradient alloys? Why gradient alloys? Gradient alloys, I'm sure you can think of your bones. Your bones is not one material all over the bone, and the property is changing based on where it is located in your bone. Always gradient components have a better performance and have like you can save weight, you can save cost. So currently, we have one material for the whole component, but now that we can print gradient alloys, and we have a big DARPA project from MIT, but we are also part of that, now we can make components gradient composition. And now that our framework that we called it Alloy GPT, this Alloy GPT can systematically give us all the solution for a target property. For each voxel, we can think of, if we need a property and we have all the solution based on other constraint, what is the best solution for this voxel? And it helps us to develop the whole menu of material which are possible for each voxel. So finally, as I said, we wanted to further accelerate the whole loops of the design. And the final thing was that currently we as a human, if you want to do the whole loop of the design, is the human who understand the problem, formulate the plan, retrieve the data from literature, apply tool, handle bugs, criticize the results, and then continue do the loop and decide what experiment. However, we wanted to replace this human with the large language model agents, and human be the leading these mixed agent team to be higher efficient by accelerating and automating the whole simulation and the whole thinking and reasoning. With that, we also developed this, use agentic AI to make this automated, and we could prompt it with let's design, for example, an aluminum silicon alloy composition that is optimized for good printability for additive manufacturing. So we didn't define what is the metric. It should go search the literature, find what is the metric, write the code, run the code, debug the code, make a reasoning, does it make sense or not, and finally save the results for us in an output file. And although all these iteration, it took a lot of iteration for the code, but I can say the whole process took less than 5 minutes. And we think that is this automation in simulation and also thinking that will bring us a huge saving of time for design of alloys. For example, consider now if a PhD student wants to do all these complex tasks, at least it takes 6 months to 1 year of training to achieve this level of coding and reasoning. So with that, this is the final slide, is that we think by now automation of the whole simulation and reasoning, and also by combining machine learning to make the computation explore the design space more efficiently, and also by automation of experiment with the robots and these agentic AI to be the brain of these robots, we can accelerate the whole loop of the design for the alloys. And initially, when there was no help from discovery to deployment of any new alloy for industry, was taking 20 years. After material genome initiative, by combining with simulation, it decreased to 7 to 10 years. And we expect by combining this physics-based model, AI and automation, this loop will be decreased to 2 to 3 years. So thank you very much for joining me in this talk. I want to first finally thank my bright postdoc and also PhD student, who without their bright mind, this success will not be possible, and also all the fundings which supported us through this these past 3 years. And with that, I'm happy to take your questions.
Thank you, Mohadeseh. We very much appreciate all of these great insights that you've shared with us today. We will now turn to our audience for questions. As a reminder, please submit your questions via the Q&A feature at the bottom of your screen. Make sure to include your name with your question. We have a few already, so let me just start with the first one. How can we ensure numerical predictions lead to experimental validation?
Usually numerical prediction and experimental validation, when there is a gap, is that in experiment, there is always a variability or uncertainty in experiment. So what it means? It means that, for example, if numeric, for example, predicts that I need this, for example, certain composition for my alloy, but when you order, for example, a powder, for example, when you make the powder, due to the powder processing, that it has its own variability, sometimes you cannot get exact composition that you were asking for. This natural variability in experiment must be considered in the simulation. And in fact, this is the part that we already consider in this UQ by our machine learning and in our forward prediction, inverse design, and performing this sensitivity analysis is the topic of the NASA project, and we have several papers. We must consider this UQ in our prediction to have a robust prediction that then will be experimentally validated.
Great, thank you. Okay, so in AM, or additive manufacturing, how do you control the cooling to get the desired microstructure and avoid residual stresses and cracking?
So to control the cooling, the AM has a high cooling rate. So by far, so the cooling rate a bit, for example, if you are in laser powder bed fusion compared to casting, the cooling rate is like a 10⁶ order of magnitude different. It's the nature of it. You never can make the cooling rate in additive manufacturing like casting. What we wanted to say is that you can benefit, in fact, this cooling rate to activate new microstructural features. But the problem of residual stress in the additive manufactured alloys also is a valid problem. So residual stress happens due to this cooling rate. This residual stress usually are controlled either by controlling the laser path. There are active research that how even you control the laser path to control the residual stress development during printing. The other thing is that they do some post-heat treatment, or the other thing is that one of the reasons, for example, we redesigned our alloy to have a high as-built ductility was exactly because of this. Because when we go to larger component, these residual stress are something we cannot get rid of it. But if the sample has high ductility, then it can tolerate it. That's why there will be no crack during the printing of the alloy. Yeah.
I see. I think this next question that just came in from Ned is related to this, although I might be not understanding correctly too, so bear with me here. So can you control the cooling rate, or does it vary over the area of the part?
So the cooling rate, when I said by controlling the cooling rate, we didn't aim to change the cooling rate to control the cooling rate, because the cooling rate of LPBF, although you by controlling the P and V a bit you can a bit change, you cannot tremendously change it. As I said, like it's 10⁶ times faster than like a casting. You can never make it like, yes, if you change from laser powder bed fusion to change it to DED, yes, you can change like maybe 1 order or 2 order by having a larger print size. Yes, you can change it, but by changing PV, you can change it, but it's not tremendously, you can change it. So, but my whole goal was that usually in our community, we are saying that because we had previous recipe for alloys, which was working with casting, which was a slow solidification. Now you use it for additive. You see those cracks and all the people are complaining, okay, there is cracks. We cannot print previous alloys. We cannot print all our aluminum alloys. My message was that, yes, we cannot print because we didn't design these alloys for this rapid solidification. We must redesign it. This is the first message I wanted to say. The second is that maybe this rapid solidification can be also useful. This was the idea of our alloy, that by this rapid solidification, we could activate new features in the macrostructure, and we achieve a strength that we couldn't achieve with a slow solidification. So this was the two things we wanted to mention. So we didn't want to say that you want to control the cooling rate during the printing. This was not the message we wanted to say. Yes.
Got it. Thank you so much. So I have 2 questions here that I think are pretty closely related. So I will share them both with you. One is from Tom, and he says, what are the closest applications for commercialization of this technology? And the other question was like, how long until a process like this will be more widely used in manufacturing? So I feel like those are pretty close questions.
Yes. So I can say we have several industrial interests. So one of the very near industry interest is vacuum pump, because for vacuum pump, in fact, you need high temperature strengths, and it doesn't have even fatigue because it just temperature goes high and it start to, so it's high temperature. So vacuum pump is one of the application, and in fact, we have industry interest. So we have also industry interest from various part of airplane and helicopter, and also various part of space components. We have a specific part from industrial component that they ask us now. They print some space component with these aluminum. So anything that you need to be strong but light. And for those things that I said, I can say the current most interest was from space and also from vacuum pump. These were the two main applications. But how long? The second question was that how long does it take? I don't, anything start from for sure, we have to, we will print it for a larger scale, although we have now some options that also have a higher as-built ductility, we have a higher strength. For sure, maybe we also need to redesign the alloy when we print at a larger scale. Maybe we see something that we didn't consider in the design. But because the whole design framework is so rapid and the whole machine learning is help us explore the design space more efficiently, we think if even we have to reconsider, and because we have a full control on the design and we virtually design this alloy, we have a full control on the knobs on the computer, we can rethink about how we should a bit shuffle some of the design to achieve the goals for larger scale. Since the paper was recently published this summer, although we have we have like a 10 to 15 industry interest into the material. Already it was published in summer, but very rapidly we got lots of industrial interest.
That's wonderful. And I think this question, you mentioned briefly space and flight being used in this with this technology. So Carl asks, will this type of AM manufacturing improve the supply of high temperature material used in jet engines and gas turbines?
In general, additive manufacturing, the first industry who adopted additive manufacturing was a space industry. Why? Because a gram matters in a space. So if you want even 1 gram, your spacecraft has been increased, it has a lot of cost. The other thing is that when a gram matters in a space, usually in a space, components are very complex shape because you want to achieve several objectives with the same component. As you see, and many of them also reach, for example, high temperature. These are the most extreme engineering applications. So therefore, many of them have a complicated cooling channels that these things have been like these components have been printed more precisely with additive manufacturing. That's why if you see, like a couple of months ago, we had a fully printed like a space components which were sent to the space. So what it means that the adoption for a space is very rapid because, in fact, is the industry that first it has a very critical application. Second, one reason is that still the printing of these components is a bit slow, but a space industry, the demand of a space industry, for example, how many shuttles, like satellites, we send per year to the sky, like 1,000, 2,000. This is something that we can achieve with the current printer. But consider if the entire car industry is 1 billion cars, so you should have a printer to print 1 billion components. So I can say the demand of a space industry also is at the current capacity of additive manufacturing. That's why this is the first industry who adopted this technology.
Wonderful. So this question is from Richard. What is the minimum qualification for a CMU student to join your research project, and how do they apply?
So we are happy. We are always have open positions, and I think the most important thing for us is a person who is interested into doing risky works, because as you see that we try to do something, and although I showed you all successful story, but all these success story were the good part of the story. I mean, when somebody do risky things which shatter the roof of properties, you should also consider it has a lot of also failure. So the most important thing I can say to join our group is that to be a person who accept to do high risk, I mean, in research. But the rest of training, we do it together as a group, and we have a lot of group activity and group culture that we learn from each other. The rest we take care of.
Yes, that's great. That sounds super collaborative and fun, even if you're failing some of the time. So this question is from Michael. So in these alloy designs, are you able to control electromagnetic properties such as magnetic permeability for motor structures or electrical conductivity for circuit components?
So in fact, there are also interests about using in my group, we have not done that. So, but there was another colleague who was working on magnetic material who also proposed that we work together. But I have not worked on that, on these magnetic, but on these magnetic properties by far. So maybe after I entered those projects with my colleague, I have more comments about that.
We can follow up with him.
Yeah.
Okay, so here's another question from Ned. Do you have some theories, models, and understanding of what the different atomic components do and how, or is the AI a black box?
So in fact, AI for us is not a black box. For first of all the connection I showed to you from processing to a structure to property, and all the connection I showed to you, we have a physics-based model. So we have a physics-based model to connect this processing to a structure to property. So we are simulation. We are performing, like, for example, CALFAT-based simulation, finite element simulation, and when, for example, in extreme environments, sometimes we do even MD simulation. So we have this connection first based on physics-based model. But when the number of like input goes high in these models, just finding the interaction between the input parameter influencing the output parameter become complicated if you just do simulation and repeat it and you want to do brute force. AI is a tool to help us explore this high dimensional space and just give us insight where we have to focus. This is not that there is an AI and we click it and it gives us the answer. This is not the case. First, our models are physics-based model. The AI is a tool which helps us accelerate this design and help us explore the design space more efficiently.
Great. So this question is also related to AI. So ChatGPT can explain its logic if you ask it to. Does Alloy GPT similarly explain the procedure that it uses to come up with an alloy composition?
Yes, exactly. This was, in fact, has been addressed in the paper. I suggest you read the paper to have a full answer. But the thing is that usually to understand how, for example, like Alloy GPT made these like connections, there are two ways usually, generally in these machine learning techniques. Either you start to talk with the program and exactly you learn from the program how it found it. This is one way. The other way is that you open the brain and see what are the connections between the brain. In fact, in the paper, we showed that we opened because these are transformer algorithm, and we opened, in fact, these algorithm, and we saw where the attention were paid. And we found out does this attention layer, it pay attention to which feature for reasoning, to which feature it paid attention for reasoning or for giving us the answer. And we compared even to which feature it paid attention to other machine learning techniques, like even data analytics, simple data analytics. We compared where it paid attention and what we learned it from simpler data analytic techniques. We saw some of them where we could also explain it with other techniques, but some of them also, when it tells us that it paid attention, was intuitive for us that why, and it make us think about why it paid attention, and we found out the physics behind that. Means that some of them we could predict what it paid attention when we opened the brain. Some of them, for example, you can also see the paper that was published in Advanced Material. For example, you will see that erbium zirconium must be high to achieve high performance. We could predict zirconium with simple data analytics, but for example, erbium we could not predict. And when machine learning proposed us, it caused us, we understood the reason physics-based that we found out erbium, if it is not in the composition, that specific phase that we are seeking for will not be formed. So I'm saying that it can also help you to find new physics, you know.
Great. So here's a question from Robert. Have you seen any problems in microvoids or lack of fusion, or any need for post-treatments with hot isostatic pressing?
That's a good question. So we already, when my student we printed this alloy, or the one that was printed in Germany, they already optimized the processing parameter that we do not have processing defects such as keyhole or lack of fusion or other type of defects. So we are already in the processing window. Processing window, we do not have these type of defects, and the density was more than 99.9%. So we didn't need hot HIP, and so we didn't apply that. But it was optimized. Even my students in the newer version, they used Bayesian optimization to optimize the parameter to achieve higher density and also hardness. Yeah.
Great, thank you. So here's another question. Given these advances, what do you foresee alloy design in the next 15 years in the US?
As I said, this was the last slide. I do believe, you see, maybe you have heard my talk somewhere else. I think this is the easiest example I can say to connect you to this also alloy design for. So consider previously only a certain people could drive cars, because driving cars need a special expertise. But now even old people can drive cars. Why? Because AI helped them. It doesn't do everything, but it helps them to drive. Yes. I also think combination of this AI with simulation to explore the design space. Combination of AI to help us, this agentic AI, to help us write the code, run the code, debug the code, even search the literature, understand the literature. I don't say they don't do mistakes. They may do hallucination. We should, as a human, we should lead the whole design. And also automation, the automation of the experiments that will be guided also with the AI. I do believe in the following years, as I said in the last slide, just the whole design cycle will be shortened, much shortened. The second is that I do believe, in my opinion, that a structural component now have one property in the whole component, and this is not at all like I don't think this is the best design, the most optimized design. We can learn from nature. No, there is no natural material that has one property all over the whole component. So I do believe the gradient alloys also will be used extensively, and the custom gradient alloys will be used extensively for various industrial applications. This is my vision. Yeah.
Very exciting. So you've talked a little bit about this already, but how, where, and what will the time savings be from the efficiency of this process allow us to do?
So, for example, you see for the aluminum alloy design that we have, consider we generated 250,000 or 500,000 data randomly. Although it was Latin hypercube random sampling to generate data. And for example, we had some target metric. We could only improve the metric 2 times, 2.5 times after 1,000,000 data. When we use machine learning techniques with only 40 samples, we could find a solution that was 3.5 times higher performance. So you can see that how much it decreased the amount of data you need, or the amount of iteration or experimental data you need to develop, or simulation data you need to calculate. So and this is one part that it helps. The second part is writing these hybrid codes sometimes, or understanding because now we have to combine different simulation together. Learning all the type of simulation code, writing the code, all these things takes a lot of time for somebody to start. But now with this like AI, you can also accelerate this process. And finally, also, I'm sure you have used ChatGPT to consult with. Literature review also it's not that it does everything, but it helps you also to do this literature review faster, even if you find your papers yourself, but help you explore this literature that you have and find useful information. It's really helpful in that. In these aspects, when it already helps, it already saves you a lot of time and go forward. And there are also many other aspects maybe I forgot, but this is the things that I remember.
That's great. Well, we do have a couple of more questions before
Sure.
we wrap up. So Richard has a follow-up or a clarification question to a question he asked earlier. So the earlier question was what was the minimum qualification for a student to join your group? And he actually was referring to academic qualification. So for example, major, degree, area of study.
So thank you for being interested into our group. In fact, our department search is, as you may know, is first the student pass the admission committee. So our department is not based on professor first. Means that all the students must pass the admission committee, and when they pass the admission committee, then the list goes to the professors. If I say for our department, for sure, if you had some exposure to research and you had exposure to some research and you have a good grades in your school, I know that these have a positive things. But if you pass the department evaluation, in my group, I think we just mainly talk, if you pass those evaluation, the only things, as I said, we only talk that we see if we can work together as a group, because all the students in my group, we choose in a way that we are working as a team, because we are in many large projects, and the most important thing that we should be able to work together very efficiently. And we see that if that person is interested to work with my group or not. This is
So I think too, Mohadeseh, is your group very collaborative, meaning from multiple departments across the college?
So first of all, we have we have a NASA project. The PI is Professor Tony Rowlett, but that NASA project is like between multiple universities. There are 19 PI in that 19 investigator, I can say, in that project. And 50 students in total, I don't know, even maybe more. And I am one of the PI. So consider the person must be very collaborative. And because these big projects usually aims for large impacts. But each person is an important piece in the whole big chain, and that person, if you will become bottleneck if you do not work with others well. So, and then we have also DARPA project, the same. We have a Naval Nuclear Lab project, the same. Now we have an NSF DEMREF project, the same. So all these projects which are large usually aim for something large. But each person contribution, not only it's important the person do your own work, but it's more important is that how you connect with others and how you work with others to be helpful, and also your results be useful for others, So that's why the group work and how to collaborate and how to communicate is very important in my group.
That's great. So we have one more question and then we'll wrap up. This is from Jim, are there any efforts to apply this to microelectronics?
No. Are there any, sorry, what was the word?
Are there any, sorry, let me pull it back up. Are there any efforts to apply this to microelectronics?
There was an interest, in fact, there was an interest from microelectronics, but this is something that was recently raised. And I know that from previous aluminum alloys, they were also interested in using these aluminum alloys for electronic application. But for this aluminum alloy we designed, there was a recent interest, but I'm evaluating. But I'm aware that for our alloy, it's a recent thing we are considering that. but if anybody else is interested, I'm happy to discuss with you. But I know that other similar alloys have been also used for electronic applications, so I know that this is viable.
Wonderful. Well, thank you again, Mohadeseh, for a very thought-provoking and informative program. I would
Thank you.
also, yeah, thank you. I would also like to thank our audience for participating today. I hope you were able to join us at future Faculty Insights programs. Please keep an eye out for a follow-up email soon, which will include a link to the recording from this session. Thank you again, and have a great day.
Thank you.